Hi, this is my second lecture in module 1 and on simple linear regression. In the first lecture, we have introduced a simple linear regression model, and we have learned how to estimate the regression coefficients using least square technique. Here is the content of today's lecture. First, we will give one example on simple linear regression, and then we talk about useful properties of least square fit, and then the statistical property of least square estimator. Let me just recall the simple linear regression model. The general form of simple linear regression model is y equal to beta naught plus beta 1 x plus epsilon, where y is the response variable, x is the regressor variable, and epsilon is the error term, and beta naught is intercept, and the beta 1 is slope, and we call beta naught and beta 1 they are they are regression coefficients. Now, given a set of observations, say xi, yi, for I equal to 1 to n, we learned how to estimate the regression coefficients beta naught and beta 1 using least square technique. So, least square method determines the parameters. Parameters means the regression coefficients beta naught and beta 1 by minimizing residual sum of square, SS residual, which is equal to E I square, I equal to 1 to n, which is basically equal to the difference between the observed response value and the estimated response value y I hat. So, this is the residual, and y I hat, this is y I minus y I hat is the is equal to beta naught hat plus beta 1 hat x. So, this is beta naught hat minus beta 1 hat x I whole square, because the fitted equation is y I hat equal to beta naught hat plus beta 1 hat x I. Okay, so we learned that beta naught, this SS residual or residual sum of square is minimum when beta naught hat is equal to y bar minus beta 1 hat x bar, and beta 1 hat is equal to summation xi minus x bar yi minus y bar by summation xi minus x bar whole square. Well, this quantity is also denoted by the symbol S xy by S xx, and this one can also be written in the form summation xi yi minus x bar y bar n times by summation xi square minus n into x bar square. This is not difficult to observe. Just a simple algebra shows that this quantity is equal to this quantity. Okay, so let us move to the Disney toy example. This is the cost on advertising and this is the sales amount. So, these are the xi values and these are the yi values, and we want to fit a straight line model to this data. This table shows summation xi equal to 15, summation yi equal to 10, summation xi square equal to 55, summation yi square equal to 26, and summation xi yi is equal to 37, and then we can compute the value of beta 1 hat. So, beta 1 hat is equal to summation xi yi minus n times x bar into y bar by summation xi square minus n times x bar square, which is equal to 0.7, and similarly beta naught hat is equal to y bar minus beta 1 hat x bar, which is equal to minus 0.1. Well, so the fitted equation is y hat equal to beta naught, which is equal to minus 0.1 plus 0.7 into x. So, this is the fitted equation for the given observations. Now, what is the interpretation of this regression coefficient beta 1? So, it says that the expected value of the response variable or expected sales amount is increased by 0.7 units for each $1 increase in advertising, and the interpretation of the coefficient beta naught hat is that what is the average sales amount when x equal to 0. So, beta naught is equal to y hat when x equal to 0. So, beta naught hat this basically gives some idea about the average value of sales amount when the advertising cost is equal to 0. So, I mean it is very difficult to explain why it is so, because see, we can expect some sales amount without advertising also, but here it is negative. Anyway, so the beta naught hat is the average sales volume which is equal to minus 0.1 when the advertising cost is equal to 0. Well, next we move to the useful properties of least square fit. It says that we know what is residual. This EI is the difference between the observed response value and the predicted or the estimated response value. So, it says that the sum of residuals in any regression model that contains an intercept beta naught is always 0. Okay, I am going to prove this one. So, the summation EI is equal to 0, and the second property says that the sum of the observed value is equal to the sum of the fitted values yi hat. So, I mean this second property is a consequence of the first property, it is obtained from this one only. Let me prove the first property, which says that the sum of residuals in any regression model that contains an intercept beta naught is always equal to 0. So, what we have to do is that we have to recall the LS method, least square method. Least square method determines the parameter beta naught and beta 1 by minimizing SS residual, that is residual sum of square, which is equal to summation EI square. Okay. And this is basically equal to summation yi minus yi hat square, and this is equal to summation yi minus beta naught hat minus beta 1 hat xi square. Well, so least square method or LS method determines the parameter beta naught hat and beta 1 hat by minimizing this quantity. So, what we do is that we differentiate the residual sum of square with respect to beta naught hat, and we equate that with 0 and we get the first normal equation. The normal equations there are two normal equations. We differentiate SS residual with respect to beta naught hat, that gives one normal equation, and again we differentiate residual sum of square with respect to beta 1 hat, that gives another normal equation. The first normal equation, you differentiate SS residual with respect to with respect to beta naught hat, that gives summation yi minus beta naught hat minus beta 1 hat xi, 2 times of this and one negative sign here. So, and we equate this to equal to 0. So, this is the first normal equation, and which is nothing but, see, this is nothing but yi minus yi hat. So, this one is nothing but summation ei equal to 0. So, the first normal equation says that the sum of the residuals is equal to 0, and this residual sum of residual EI is nothing but summation. So, this is the first property. The second property says that, well, so this is sum of residual is equal to yi minus yi hat. This is the residual, ith residual, and we know this is equal to 0 from the first property, which implies that summation yi is equal to summation yi hat. So, this one is a consequence of the previous property or the first property. It says that the sum of observed values is equal to the sum of the fitted values. Well, so next move to the third property. It says that summation xi ei equal to 0. That means sum of residuals weighted by the corresponding value of the regressor variable is equal to 0. So, sum of residual EI weighted by the corresponding value of the regressor variable, this is the value of the ith regressor variable, this is equal to 0. And the fourth property says that summation yi hat EI is equal to 0. That means, the sum of residuals weighted by the corresponding fitted value of the response variable is equal to 0. Well, let me prove these two properties, property 3 and property 4. By differentiating this residual sum of square with respect to beta naught hat, we got this normal equation. This is the first normal equation. Now, again we differentiate this normal equation, this sum of residual with respect to beta 1 hat, and that gives summation yi minus beta naught hat minus beta 1 hat xi, and we are differentiating with respect to beta 1 hat. So, this quantity will be multiplied by minus 2 into xi. So, minus 2 into xi, which is equal to 0. This is the second normal equation, and this one is nothing but summation yi, and this part is yi hat into xi equal to 0, which implies summation ei xi equal to 0, which is the third property. Now, the fourth property is summation ei yi hat, this is equal to 0, but summation ei yi is not equal to 0. You should note that. Okay, how to prove that summation ei yi hat equal to 0? This is again the consequence of the first property and the third property. This can be written as summation ei. What is yi hat? Yi hat is equal to beta naught hat plus beta 1 hat xi, which is equal to 0. Okay. Which is equal to summation beta naught hat ei plus beta 1 hat summation ei xi. Now, see, summation ei from the first property, this is equal to 0. So, this is equal to 0 plus the third property says that summation E I x I equal to 0. So, this is basically beta naught hat into 0 plus beta 1 hat into 0. So, this is equal to 0. So, we proved that summation E I y I hat equal to 0. Okay, so, these are the some properties of least square fit, and we will be using them in future. Next, let's move to the statistical properties of least square estimators. So, we have estimated the regression coefficient beta naught and beta 1 using least square estimator, and we are going to prove that both beta naught hat and beta 1 hat are unbiased estimator of beta naught and beta 1 respectively. Well, let me prove that. First, I will prove that beta naught hat and beta 1 hat are linear combinations of observations. Y I. That means, we want to say that they are linear estimator. Okay, for example, consider beta 1 hat. So, what is beta 1 hat? Beta 1 hat is equal to summation x I minus x bar into y I minus y bar by summation x I minus x bar whole square. Now, I said that this is a linear combination of the response variables y i's or the observations y i's. Okay, so this can be written as summation x I minus x bar into y I only by summation x I minus x bar whole square. This is easy to, I mean, these two quantity are same. One can very easily prove that summation x I minus x bar into y bar, that quantity is equal to 0. It is not difficult to prove that. Now, this is from I equal to 1 to n and I equal to 1 to n. Now, this can be written as summation C I y I, where C I is equal to, here I equal to 1 to n, where C I is equal to x I minus x bar by summation x I minus x bar whole square. So, I proved that beta 1 hat is a linear combination of the observations y I. Similarly, one can prove that beta naught hat is also what is beta naught hat? Beta naught hat is equal to y bar minus beta 1 hat x bar. So, this is also a linear combinations of the observations, because see this is nothing but summation yi from I equal to 1 to n and minus beta 1 hat x bar. We already proved that beta 1 hat is a linear combination of the observations yi, and the first term is also a linear combination of yi. So, the whole thing is a linear combinations of the observations yi. Okay, so, this just proved that the estimator we got, they are linear estimator, they are linear in yi. Next, let me prove that the estimator beta naught and beta 1, they are unbiased estimator. That is, we are going to prove that expectation of beta 1 hat is equal to beta 1. So, if this is true, then we call beta 1 is an unbiased estimator. Okay. Let me start from here. The simple linear regression model is yi is equal to beta naught plus beta 1 xi plus epsilon I. Okay. Now, y bar which is equal to summation yi I equal to 1 to n, this is equal to beta naught plus beta 1 xi will be replaced by x bar and epsilon I will be replaced by epsilon bar. Okay. So, where x bar is of course equal to summation xi 1 to n and epsilon bar is also equal to summation epsilon I 1 to n. Okay. Then from here yi minus y bar is equal to yi minus y bar is equal to beta 1 into xi minus x bar plus epsilon I minus epsilon bar. Okay. So, the expected value of yi minus y bar is equal to, see one thing you should observe, that you should always remember that y is a random variable, the response variable y is a random variable, but x is not a random variable, it is a controlled variable. So, for given I, this is just a constant. Okay. So, expected value of yi minus y bar is equal to beta 1 xi minus x bar plus expectation of epsilon I minus epsilon bar. Now, epsilon I is the random error which is a random variable, and this follows, we assumed that epsilon I follows normal 0 sigma square. So, the expected value of ei is equal to 0, and similarly the expected value of epsilon bar is also equal to 0. So, the expected value of yi minus y bar, this term is going to be 0, is equal to beta 1 into xi minus x bar. Now, our aim is to prove that beta 1 hat is an unbiased estimator of beta 1. So, expectation of beta 1 hat is equal to expectation of, what is beta 1 hat? Beta 1 hat is equal to summation xi minus x bar yi minus y bar by summation xi minus x bar whole square. Okay. So, this one is nothing but summation xi minus x bar into expectation of yi minus y bar by summation xi minus x bar whole square. Now, note that we proved that expectation of yi minus y bar is equal to beta 1 into xi minus x bar. So, expectation of beta 1 hat is equal to summation xi minus x bar, and this quantity is equal to beta 1 xi minus x bar by summation xi minus x bar whole square. So, this is nothing but beta 1 only, because this one is nothing but xi minus x bar whole square. So, we proved that beta 1 hat is an unbiased estimator of beta 1. Similarly, next we prove that beta 1 hat, beta naught hat is also unbiased. That means, we are going to prove that expected value of beta naught hat is equal to beta naught. So, this is equal to expectation of y bar minus beta 1 hat x bar. Okay. So, what is y bar? Y bar equal to, we proved in the previous slide that y bar is nothing but beta naught plus beta 1 x bar minus beta 1 hat x bar. So, this is equal to expectation of beta naught is beta naught, expectation of beta 1 x bar is equal to beta 1 x bar. Now, the expectation of beta 1 hat, just now we proved that the expectation of beta naught beta 1 hat is equal to beta 1 hat, beta 1. So, this is equal to beta 1 x bar, which is equal to beta naught. So, we proved that both beta 1 hat and beta naught hat are unbiased. Okay. Next, we will talk about the variance of beta 1 hat and beta naught hat. The variance of beta 1 hat is equal to sigma square by S x x, and the variance of beta naught hat is equal to sigma square into 1 by n plus x bar square by S x x. Anyway, I mean we need to know how to derive these things. Well, so next we talk about the variance of beta naught hat and beta 1 hat. Okay, so the variance of beta 1 hat is equal to the variance of, what is beta 1 hat? Beta 1 hat is equal to summation xi minus x bar into yi minus y bar by summation xi minus x bar whole square. Okay. Well, now this can be written as the variance of summation xi minus x bar into yi by summation xi minus x bar whole square. And this is nothing but, see, I before also I proved that this estimator is a linear combination of the observations yi. So, the variance of this quantity is and since yi's are independent, you know, well, so this is equal to variance of summation ci yi, where ci is equal to xi minus x bar by summation xi minus x bar whole square. Now, we know that the variance of summation ci yi is equal to summation sum of variances ci square variance of yi. This is true because yi's are independent, and we know that variance of yi is equal to sigma square. So, this is equal to summation ci square sigma square. Now, what is summation ci square? Summation ci square, we know this is ci. So, variance of beta 1 hat is equal to sigma square into summation ci square, which is equal to summation xi minus x bar ci square. So, summation xi minus x bar whole square by summation xi minus x bar whole square and square of the whole things. So, I am just replacing C I square by its value, and this becomes sigma square by summation x I minus x bar whole square. Which is equal to sigma square by S x x by notation. So, we proved that variance of beta 1 hat is equal to sigma square by S x x. Okay. So, next we talk about the variance of beta naught hat. Variance of beta naught hat is equal to variance of y bar minus beta 1 hat x bar, right. Now, this variance can be written as the variance of y bar plus the variance of beta 1 hat x bar minus 2 times x bar the covariance of y bar and beta 1 hat, right. Now, you know the variance of y bar, I hope you know it. It is equal to, it is not difficult to prove that this is equal to sigma square by n. Let me prove this. Variance of y bar is equal to the variance of 1 by n summation y I. Now, y i's are independent, that is the assumption we made at the beginning, because e i's are independent. So, epsilon i's are independent. So, y i's are also independent. So, the variance of this quantity is equal to summation of variance of y i's by n square, right. And variance of y I is equal to sigma square. So, summation sigma square n times 1 to n by n square. So, this is basically n sigma square by n square. So, this is equal to sigma square by n. The variance of y bar is equal to sigma square by n. We know the variance of beta 1 hat, and this is a constant quantity. So, the variance of this quantity is x bar square into variance of beta 1 hat, which is equal to sigma square by S x x, just we proved. Now, what about this covariance? This is going to be, this covariance is going to be 0. So, this is 2 x bar into 0 into 0, but we need to prove this one. Okay. The covariance between, this can be proved that the covariance is equal to 0. The covariance between y bar and beta 1 hat is equal to the covariance between, what is y bar? Y bar is equal to summation y I by n, and beta 1 hat is equal to summation x I minus x bar into y I by summation xi minus x bar whole square, right. Now, this covariance is, see, yi's are independent. So, the covariance between yi and yj is equal to 0 when I is not equal to j. So, this is nothing but the summation of xi minus x bar, the covariance between yi and yi. So, which is nothing but the variance of yi, right, by summation xi minus x bar whole square and one n here. So, this is equal to summation xi minus x bar, variance of yi is equal to sigma square by n into summation xi minus x bar whole square, and this quantity, see, summation xi minus x bar is equal to 0. That is why the numerator is 0. So, this is equal to sigma square into summation xi minus x bar. This quantity is 0 always by n into summation xi minus x bar whole square. So, this is nothing, this is equal to 0 because of the fact that summation xi minus x bar is always equal to 0. So, we proved that. So, we proved that the covariance is equal to 0. That means, the variance of beta naught hat is equal to sigma square by n plus x bar square and the into variance of beta 1 hat, which is equal to sigma square by s x x, which we just proved. So, this is equal to sigma square by into 1 by n plus x bar square by s x x. Okay. So, we found, so we proved that both beta naught and beta 1, they are unbiased estimator of sigma square, and also we proved that the variance of beta naught hat is equal to sigma square 1 by n plus x bar square by s x x, and the variance of beta 1 hat is equal to sigma square by s x x. So, now see, both the variance formula, the variance for beta naught hat and beta 1 hat, both involve sigma square. So, but we do not know what is the value of sigma square. So, sigma square must be replaced by its estimator. So, we need to estimate the value of sigma square. So, next we talk about the estimation of sigma square, how to estimate sigma square. Estimation of sigma square. Well, the estimation of sigma square is obtained from the residual sum of square, SS residual, and finally, we will be proving that expected value of SS residual by n minus 2 this thing is equal to sigma square. That means the sum of residual sum of square by n minus 2 is an unbiased estimator of sigma square, and will be we can compute the value of residual sum of square given a set of observations, and we know n. So, using this formula we can estimate the value of the population variance sigma square. Well, so we need to prove this one. SS residual is equal to summation EI square, that we know, and which is equal to the difference, the ith residual is the difference between ith observation and the estimated value yi hat. Okay. Well, so this is equal to square here. This is equal to summation yi minus what is yi hat is equal to beta naught hat minus beta 1 hat xi whole square. Okay. So, what we do here is that we know that beta naught hat is equal to just trying to find a convenient form for SS residual. So, beta naught hat is equal to y bar minus beta 1 hat x bar, right. So, we will just plug this value here. This is equal to summation yi minus y bar minus beta 1 hat xi plus beta 1 hat x bar whole square. Okay. So, this is equal to summation yi minus y bar minus beta 1 hat xi minus x bar whole square. Now, this can be written as summation yi minus y bar whole square minus, okay, let me write plus beta 1 hat square summation xi minus x bar whole square minus 2 times beta 1 hat summation xi minus x bar into yi minus y bar. Right. So, this can be written in the form SYY plus beta 1 hat square SXX minus twice beta 1 hat SXY. Just notation. Now, see, we know that beta 1 hat is equal to SXY by SXX, right. So, what I will do is that I will replace this SXXY by beta 1 hat into SXX. So, this is equal to SYY minus beta 1 hat SXX minus twice beta 1 hat. Now, replace this one by beta 1 hat SXX into. So, this becomes SYY plus beta 1 hat SXX minus 2 times this is square here beta 1 hat square s x x. So, which is equal to s y y minus beta 1 hat s x x. So, this is the convenient form of SS residual, and we are going to use this one in the next class to prove that, because we need to find the expected value of this one to prove that expectation of SS, to prove that expectation of SS residual by n minus 2 equal to sigma square. Well, so we will continue in the next class. Thank you.